welcome. And Mark, thank you for that wonderful introduction. It actually gets to shave about 30 seconds off of my introduction because you did such a wonderful job introducing me. So thank you. And I'm delighted to be here. And actually, in fact, delighted to be here once again, as usual. Always a pleasure to speak at any event that Mark is hosting. And there's a link for you, a bit.ly link. You can visit that link. It's all lowercase, pass hybrid underscore cosmos underscore CF for change feed. That will take you to my OneDrive, which will, and from there you can download a zip file that has this deck and all the code, tons of code, actually more code than we'll cover today, but certainly all of the code that we'll cover today. So without further ado, I'm going to jump right in. So what are our objectives? Well, I'll start by saying this is somewhat of an advanced course, but I'm really, and if you have some background in Cosmos DB, that can be helpful, but I'm not going to make that an absolute requirement because I'm going to review at least the minimum core concepts that you really, the critical core concepts, namely partitioning, in order to level set. And then we'll talk about the change feed and learn all about what it can do for you, and we'll put it all together with microservices. So we'll apply all of the concepts around partitioning in Cosmos DB and the things you learn about the change feed to build what we're calling event-driven microservices. And we'll define microservices a little bit better right now, but first let's talk about the change feed. We have a container, and anytime we insert or update a container, and soon even when we delete an item to a container, rather, that gets emitted through the change feed. And that opens up a wide range of scenarios because you can subscribe to that change feed and pick up these changes in near real time. So you can do things like replication, denormalization, notifications, materialized views, moving data. All of these things are very possible, and they're not actually necessarily new concepts, but very often we build these monolithic traditional applications with these tightly coupled components with a lot of interdependencies, and it's often a much better model to instead go with what's called a microservices architecture, where each of these are really completely independent from one another and have no dependencies on one another. And you could have microservices in each of the categories shown here. You could have several notification microservices and several materialized view microservices, and is any number of these, or many number of these independent microservices, all consuming a single bus, if you will, a single event bus, which is the Cosmos DB change feed. And that makes for a much simpler architecture overall than if you had all of these interdependencies with all these components communicating with one another. So, like I said, we're going to level set with horizontal partitioning and make sure we have a clear understanding of what that's about. If you were at my session in June, this will seem a little bit familiar, but if you're new to Cosmos DB, it's important to understand that while we store data in a container, and we think of this as being just one container that we read and write data to, that there is in fact a bank of servers, a cluster of physical boxes or physical partitions, if you will, that just grows elastically on demand as your scale, as your need to scale grows, right? As you have more storage and more throughput requirements, because each one of these physical partitions is really just a physical computer, each with its own CPU and fixed disk capacity, but there's certainly no upper limit on the number of servers in the cluster, and therefore, if you partition things correctly, you get virtually unlimited storage and unlimited throughput with this approach, right? And it's very important to understand what logical partitions are. So we have this bank of servers sitting behind each container. Like I said, we don't really need to concern ourselves with them much, but if we just drill in a little bit and realize that when we write to our container, these are JSON documents and they could land on any physical partition that's behind that container. And so how does Cosmos DB know which physical partition to store a given document? The answer to that question has to do with logical partitions, and that's what we define. So Cosmos DB manages the physical partitions, we manage the logical partitions. How? By choosing a partition key. And this is the most fundamental, most critical concept in Cosmos DB. This will make you or break you if you pick the right choice or the wrong choice. If we went with and I'm just going to go with a social network scenario, a Facebook, LinkedIn style site, We might partition on the username, and that would mean, therefore, and if we, just forget about the physical partitions and just focus on the logical partitions, every user's documents will be in a logical partition for that user. And of course, these documents don't all have to be of the same type. You can, imagine one of them would be a user profile document, and then there would be potentially great many number of blog post documents, and then documents of other types, like documents representing likes or comments, that all have different schemas, but what they all share in common is they have that same username property. That's the partition key that's kind of grouping all of those documents together in the same logical partition. Now, I don't think I covered this in June, so this is something just drilling a little bit deeper, since we will be seeing different partitioning patterns, and I'm by no means being exhaustive. This is really should do an entire topic on just partitioning, but it's it's very common to actually partition on the ID property. So that seems strange to people. At first, it seems odd to use the ID property as the partition key. I'll take a step back and make sure that it's clear that every document that you write to a container is going to be unique within that container based on a composite, a combination of this ID property here, and then whatever property you choose to be the partition key. So if you choose the ID property itself as the partition key, you wind up with a situation where you're never going to have more than a single document inside a logical partition. And I say that this is common in write-heavy scenarios. It could also be common in read scenarios where you only are typically reading a single document at a time, and you always know its ID, like what are called point reads. But certainly for ingesting a high volume of data, like which you have for IoT scenarios, I don't care how active we are on social media, we don't come close to the telemetry that comes out of the airplanes and automobiles and elevators and sensor data and all that sort of thing. And Cosmos DB does a great job at ingesting this mass volume of data at high velocity. And the best way that you can facilitate that is by partitioning on the ID property, so that from a write perspective, you are going to achieve the largest spectrum of values, the most unique number of partition keys, right? But of course, if you think about it in scenarios where you need to query against this data and where you don't know the ID, let's say the ID is a GUID, right, which is very often the case, then you don't know the ID, so you need to run a query, but that's a problem, even if it's just for one document, certainly for more than one document. And we'll talk about how we resolve things like that. Now, it's also common to use the type property. Now, I shouldn't call it the type property. Yeah, I can call it the ID property the ID property, because every document has to have an ID property called ID that behaves the way I described. In combination with the partition key, it's what defines a unique document in the container. But it's good practice and very common to always have a type property. And then if you have like small lookup lists, and to always, set the type property to help you like identify the schema, because we're in a schema-free world. But if it's a small lookup list, and when I say a small lookup list, I mean anything that fits comfortably into 20 gig or less. So, my IoT telemetry data obviously won't fit in a single logical partition, but the metadata that I have, like my list of flights that I run, or the list of airports that I service, or the product categories on my e-commerce website, and tell me what application doesn't have a list of states and provinces and so on, that sort of thing, where you don't need this massive scale, but you still need to store this information in the database. It's very common to partition on the type property and just set that type property to the same value in every document. So every flight document has a type property set to flight, and so on. And if you partition on the type property, that is going to make it very efficient for you to retrieve that list, in its entirety or any subset of it, because it's all in a single logical partition. And then, like I said, it's an exhaustive subject. I'm going to just use for an example. If you were at my session last time, you might remember that we had an e-commerce scenario where we had customers and orders, and customer ID was the best partition key, because we could query for a customer and get all the embedded information about that customer and all of the related orders. Given the lack of joins in a NoSQL world, the equivalent would be saying we get it all in a single logical partition, so you get them all together. And the list goes on and on. I mean, there's just many different ways, to partition your data depending on your scenarios. So I think we're doing pretty good on time here. It's very critical to talk about, in many cases, it's very critical to talk about the order of the change events and the guarantees that you get or don't get with the Cosmos DB change feed. So just like, I mean, I introduced the change feed already as this one thing that you subscribe to get all of the changes that are made to the container. But right behind the container, you have multiple physical partitions. So the reality is that each physical partition has its own change feed, okay, under the covers. So that I'm going to describe now a scenario where we're modeling a shopping cart scenario that's event-based, meaning I'm not modeling state, I'm modeling events. So it's in a schema-free world, you're free to model data any way that you see fit. So in this scenario, there are only inserts. Even when a user removes an item from the cart, that's just another insert representing that event. So if I partitioned on the cart ID property, or with the order ID property, whatever you want to call it, for this session, right, where the first session, the first cart is opened up and the first event occurs because the user has added an item to the cart, and then another user has added another item to another cart. So in this particular case, Cosmos DB has created separate logical partitions. Well, we knew it was going to be separate logical partitions because we defined the cart ID as the partition key, but the fact that one is on one physical partition and one is on the other, that's not relevant to us, and that is just what Cosmos DB has gone ahead and done. But at the same time, it's also, as you see on the bottom portion of the slide, emitted those events to the change feed. So this goes on now, and then a second event occurs, and then again, this could either be another item was added to the cart, or the first item was removed, or the quantity on the first item was changed, but it's the second event for the cart, and it goes on for the third customer and the fourth customer, and this goes on to a point where at some point Cosmos DB is going to need to scale, right? I mean, it's going to be long before two logical partitions, but the whole point is that you don't have to worry about this scale out that happens automatically for you. So at some point, Cosmos DB is going to need to perform a split. It's going to say, okay, not necessarily when it runs out of space from a disk storage perspective, by the way. It could also be from a throughput perspective based on the number of RUs that you've provisioned and are paying for. They might need to add more physical partitions to guarantee their SLAs, right, for that provision throughput. So when Cosmos DB needs to scale out that container behind the scenes, it will literally split a single physical partition without disturbing any of the other physical partitions. And when I say split, I mean, well, first of all, it'll create a new physical partition which has its own change feed, right? And then it will literally move roughly half of the logical partitions. I only have space to show one, but it would be roughly half of the logical partitions that used to be on physical partition 2 are now on physical partition 3. And this happens instantaneously behind the scenes. And at the same time, when that occurs, the events that were recorded in the change feed are migrated over at the same time as well. And what you can see is that now we're able to continue growing. So we've got another customer, and then the events continue, and so on and so on. But what you can see, ultimately, even though these individual customers are firing off events overlapping one another, their order is guaranteed in each physical partition. So the events, when they were moved over from partition 2 to partition 3, their order was also preserved. So if you were to now process these in order, because you can always rewind the change feed and replay the change feed, which is a critical concept. It is a persistent event store because it is built and baked into Cosmos DB. You're always going to be guaranteed that you're processing the cart events in the order that they occurred, even as they're interleaved, these events, and even as partition splits occur dynamically behind the scenes as users are shopping. So again, of course, fortunately, you don't really have to really consume 3 change feeds. Just like you don't concern yourself with the physical partitions and you just think of one logical container, you can thankfully, because with the help of the change feed processor library, you can view this as just one logical change feed. So if you, even if you were to interleave these and parallelize them, which is another big benefit. So the CFP library, change feed processor library, which I'm calling the CFP library, will also parallelize across partitions so that they could be interleaved like so. But if you process these events down in order, even as the carts themselves are in jumbled order, the events per cart are not. And that's what's critical, right? Because you need to think of a large-scale order processing pipeline where you have individual microservices that are watching the events as they occur, and one of them is calculating tax, and one of them is updating inventory, and one of them is handling payments, and surely the pay, you can't start, and one of them actually starts the fulfillment, which obviously surely that will be in response to the user checking out their cart, but surely that has to be the last event. There, you can't get the events out of order because you can't get, after they check out their cart, you get a late event saying, oh, by the way, an item was removed, and now you're fulfilling an order for an item that the user removed from their cart. Hopefully that's clear, because that is really a critical concept. But now we can just jump right into consuming the change feed. How many different ways can you do it? Well, there's actually 4 ways. I have to update this slide. I'm showing 3 on this slide, and the first you would not want to do. I mention it because it is technically an option, but like you only do this unless if pain is something that you enjoy, because it's very difficult. You have to manage, you have to do a lot of work. You have to look at each of the individual physical partitions, change feed, and keep track of when you last queried each one for changes. And then you need to scale out yourself, and you need to manage partition splits as they occur. And all of these housekeeping and tasks that I'm describing, if you want to achieve real scale, you don't want to have to do by hand. So that's why you want the CFP library. It does all those things. That's why I mentioned them. It will give you a stateful and scalable solution. So it will keep track of the physical partitions. It will remember the last time it queried for changes on each physical partition behind the scenes. It will manage splits transparently, and it will scale on it also as well as Cosmos DB scales your container. The CFP library will scale your change feed processing of that container. And then the third way, and this is actually all of these are just increasing levels of abstraction, Azure Functions. So the change feed processor library wraps the direct underlying plumbing to the physical partitions, and Azure Functions just gives you a serverless wrapper and just makes things even easier in terms of deployment. And if you're not familiar with Azure Functions, you will be by the end of this session. I'll talk a little bit more about them as we see them in use in the demos. But understand that it's not a choice between the two. So all the aforementioned benefits that the CFP library gives you in terms of state and scale, you will get with Azure Functions as well. Plus the benefits of serverless deployment, meaning you don't really have to manage a VM or a cloud service or a web service, to host this thing. You can just deploy the functions themselves. All right, so that's enough background. I'm going to jump into our first use case. If you remember, I listed a bunch. Replication, denormalization. There were a bunch there, and we're going to go in order. We are actually in tackle each one of those use cases in this session, starting with the first one, which is replication. So you have to choose a partition key. Hopefully, I've impressed on you the importance of choosing the right one. You're going to have to really understand how your application and your users are querying your data and what those patterns are in order to make the best choice. But ultimately, what happens if you can't, you can't choose just one. You can only choose one, but ultimately, after all the analysis, it turns out that roughly half the time you're querying this data set based on one partition key, and the other half the time on a different partition key, and you really cannot have 2 different partition keys. Don't think you can have a composite, and it's not going to help you. You can't really defy the laws of physics in terms of how you're physically partitioning things in logical partitions. So this can be a problem if you have heavy reads on both patterns, and really only if you have heavy reads on both patterns. The occasional cross-partition query is not going to be compelling enough reason to do this. There's going to be you are going to pay the RUs to replicate the data, but you're going to save many more RUs by then having two sources of the same data, each partition for two different, I should have that up there because that's exactly what this use case is about, right? So hopefully that's clear. Let's see how that's going to work before we jump into the demo. Let's say I've got, and now I'm looking at a shopping cart document. This is actually state, not an event. Not that it matters. Well, actually, it does matter because in this scenario, we have inserts, updates, and deletes, right? So in an event-based data model, right, you will only have inserts. Like in the IoT scenario, we're going to see it soon, flight telemetry, right? There's only inserts. It's just constantly pumping inserts, right? But in this case, it's stateful, right? So there are going to be inserts, updates, and deletes. And when I first insert this document into the cart, and I'm going to partition on the cart ID, so all of the items belonging to the same cart are going to be in the same logical partition. That makes sense, right? So if I run a query like this, I'll get all the items in that cart, and I could certainly further filter on all the items in the cart by quantity or product, and that would still be a single partition query. That would be good. That would be fun because the partition key is known, and we could route the query to, directly. We Cosmos DB could route the query directly to the known logical and physical partition where this documents can live. But what if it's also very common to query on item, where you, and I mean very common, and you're hitting these queries hard. By the way, another good example is a user document where you're using it to log in, but there's a username property and there's an email address property, and you're having thousands of reads per second with in terms of login activity, and half the time it's one and half the time it's the other. That's kind of another use case. But here in this case, let's say it's very common. I need to get all of the Surface Pros across all carts, and it's a very common query. Well, in that case, we'll create a cart by item container, and we'll partition on that item property, and we'll listen on the change feed, and to be more accurate, our microservice will listen on that change feed to push that document over. But of course, in this container, that very same document is partitioned on that item property, Surface Pro, and so that second query can be satisfied by the second container, by the replica container, as a single partition query for all Surface Pros across all carts, right? Now, this is something that's important to understand. That processing updates and deletes, at least today, interim updates are not retained by the change feed. That means if you update the same document multiple times, you replace it multiple times, you're going to lose the interim updates. This is going to change. They've announced this is going to change. For our replication scenario, it doesn't matter because we only need the latest version of a document. And if we ever lose our replica and have to rebuild it from scratch by rewinding the change feed, then again, we'll only need the latest version of any document that might have been updated multiple times. So that's fine. But if you do need those interim updates, that's a capability that will be available soon, but it's not going to impact us here. What will impact us here is the fact that deletes are not written to the change feed. So what happens when I want to delete a document? How are we going to handle that? We're going to resolve that by using our time to live, our friend time to live. I'm going to show you how that works, first on the slide and then in the demo. So if the quantity on the left changes from 2 to 3, like you can see in green, we're going to change it on the right side as well, right? Because we're going to see it on the change feed. And then if the quantity gets updated from 3 to 4, we'll see that change as well. But now when we want to, the user removes this item from their cart, and therefore we actually want to delete this stateful document. We can't just delete it from the container on the left, because if we do, it will remain in the container on the right, and we'll have orphan documents, and we won't be in sync. So what we'll do instead is we will attach a time to live. And here I'm allowing 60 seconds, which is very generous. If your microservice is up all the time, it's near real time that it's going to get picked up. But a microservice could be down. It might actually be smart to set this TTL for several hours if it's common for your microservices to go down. Because you don't want to wait too long because Cosmos DB is going to delete that document on the left in 60 seconds. But meanwhile, you pick up that update and you simply delete the document immediately on the right and let Cosmos DB 60 seconds later, or however long or later, remove the document on the left. Excuse me. Okay, we're going to see how that works in a demo in a second. But we're only going to use Azure Functions. I mentioned the CFP library. I have a demo that shows the basics of the CFP library, but I'm not going to show it in the interest of time. Azure Functions are the way we're going to go, but it's very similar. there's nothing you can do in Azure it's very similar. You write one, you get a push model. You sit idle and wait for a change. But with Azure Functions, it's serverless. You write and deploy individual functions that just react to the event of triggered that gets triggered by the change feed. An important difference between the CFP library and Azure Functions, though, is that Azure Functions is, of course, shared capacity and gives you, and it's consumption-based, and you can have cold restarts for being idle for too long and unpredictable, all the unpredictability that comes with that. Whereas if you go with the CFP library, it'll be, like I said, either a VM, a web job, a worker role, whatever it is, a cloud service, something that, will give you the dedicated capacity that you can provision. With Azure Functions, you're susceptible to cold restarts. Unless you go with Azure Functions Premium, which is nice. It's just nice to know that that's there because you can get get and pay for and get that same dedicated capacity while still enjoying the serverless benefits of Azure Functions. All right, it's time for our first demo. Our replication microservice. So I'm going to just jump right in to the Azure portal, which I've got here somewhere. Yeah, there we go. And I'm going to show you that I've got this Acme Web Store database. It's going to be the same scenario we saw on the slide. I've got a cart container that is currently empty. Okay, and this is a problem that I've noticed when I do screencasts with the web portal. When you click on items, there's a terrible delay. That one wasn't too bad, but if you look at scale and settings, you can see that we're partitioned on the cart ID, right? So that's the container on the left that we saw. All right. Now, what's this lease container? That is where the CFP library, which is again Azure Functions is using under the covers. That's where the CFP library is storing its state, and we will drill into that shortly. But right now, we just know that we have an empty cart container that's partitioned on the cart ID. So I have this notebook. I don't call them Jupyter notebooks anymore. I just call them notebooks because many languages are now supported, not just Python. But if this is Python code here that is very simple, so don't worry if you're not familiar with Python. You can read this, right? We are getting a reference to the Acme Web Store database, and we're going to create another container that's our replica container called cart by item that is partitioned on the item property because that's what we need the replica container partitioned on. And then I'm going to add 2 documents just to the cart container. So let's go ahead and do that. Right. Okay, and that's done. And now I'm going to run this SQL magic query against the cart container, the container that we just loaded 2 documents into, and you can see them there. But when I query the cart by item container, of course, it's empty. So now this can seem a little strange. It looks tabular here, I know, but don't make no mistake. It's just the representation when you're using notebooks and you're using this SQL magic here. These are actually the JSON documents, okay? These are JSON documents that are just being made to look like rows in a table, all right? So, and of course, our replica container is empty. So let's go ahead and start our replication microservice, but before we do that, why don't we take a look at it? So here in Acme Web Store, I see I've got change feed functions, and there is my replicate cart function. And even if you've never used Azure Functions before, this will be very easy to grasp. All you do is decorate a public function with the function name attribute, and that makes it an Azure function. And then that Azure function needs to be triggered by any number of available triggers, and the one that we're interested in, of course, is the Cosmos DB trigger, which says I want to watch this container in this database for changes. And this is just the old name for container. Unfortunately, they haven't changed that. It's really, we don't use the word collection except when we're talking about the MongoDB API anymore much. You should, so what we're doing is we are watching the cart container for changes. And here's the connection string information for that container. And that is when you're developing locally, stored in local settings JSON. But this is only for local development, as you can tell from the name, local settings JSON. So that means when you deploy this Azure function, you need to deploy this configuration as well. This is like app config or web config or app settings, for Azure functions. And there is a pointer to my account That's the lease container, which, like I said, we don't have to worry about. We just have to give it a name, and it's very common to just name it lease. And we will look at the lease container more in a moment. And then there's a lease collection prefix, which we'll also look at together more in a moment. I'm not going to talk about it now, but you can see it's named after the function itself. So that's really all there is to it. This is all declarative. All you get and all you need are these two parameters: the documents that changed and something that you can write output to. And right inside of here is like the sky's the limit. You can do whatever you want. So what are we doing? We're doing that very simple logic. You can see I've got a Cosmos client that I'm going to use for writing to the target container. It's going to get initialized with the same connection string because it's it's the same account. And I'm just looping through all the changes. I'm not worrying about parallelism here. If I get flooded with changes, multiple instances of this code will run automatically, so everything has to be thread safe. But I don't have to worry about the work, doing any work to parallelize or to manage state. I just respond to the change. I get a reference to my target container that I want to write to, and I go through all the changes. And it's very simple. It's going to be one or the other. Either time to live, that TTL property, okay, which actually I didn't show you, so I'm going to just flip on back to the portal for a second. And if you look at this card container, actually, let me refresh here. So we can see the cart and the cart by item container. And I look at scale and settings. You can see that time to live is enabled. It's not off. And what that means is if I put that TTL property in a document, it will auto expire. Okay. And that's always called TTL. It's called time to live in the .NET SDK just because it's giving it a friendly name. If you take a closer look, you can see that this time to live property is actually mapped to the TTL JSON property of each document. So basically I'm testing, is the intent to delete because the TTL was set? If it's null, it means it wasn't set. The intent is to either insert or update. Fortunately, there's a handy upsert item method that does that work of figuring out whether it's an insert or an update for me. So I just call update. And if there is a time to live, that means that it's going to auto expire on the source side. We need to delete it on the replica side. That's very easy to do by calling delete item async. You need to know two things to delete an item. The same two things you need to know to do a point read: the document's ID and its partition key. We know that this target container is partitioned on the item property, so we get this retrieves the item property from the document in memory, and this actually deletes the document by its ID and that partition key. And it's as simple as that. So let's give it a run. I'm going to set that as my startup project. It already is. I'll press Control F5. And being a little sluggish here, but oh yeah, no, you gotta be kidding me. I hope this doesn't make us wait, because if it does, I'm just gonna jump ahead and come back. Yeah, okay, no, we're good. We're gonna see some nice ASCII art for our Azure function that's running locally. Also, in the interest of time, I'm not going to deploy these Azure functions. I think you saw, if you were at my June session, you saw that for the denormalization. And the application is started. I can see my replicate cart function. I can also see my denormalized product function, which is coming next, but nothing seems to be happening. So I wrote two documents to the container. They are persistently written to the change feed. Why am I not picking them up? Because by default, Cosmos DB looks to the lease container and only picks up the changes from the last time it checked. And the very first time you run this and the lease container is empty, which was the case here, it's just going to start from this moment forward. And so if that's not what you want, we'll just add start from beginning equal true. And fire that up again. Control F5. Let that function fire up. And there we go. Executing replicate cart. Now these are showing up in yellow. This is my little hack. You might have noticed, I didn't point it out, but I'm logging these warnings. They're not warnings, and you don't do this in production, but it makes it easy to see because it paints it yellow. And especially when things fly by very quickly, it's just, I find it handy to see the yellow to know that it's my output. But obviously that's a hack. But there, you see now I picked up the 2 documents because I said stop from beginning equal true. So now let me close this and start it up one more time. What's going to happen? Will it pick them up again? So I'll answer that question. The answer is no, even though start from beginning equal true is still there. That is the behavior if there's no state in the lease container. But once it picks up those changes, it writes that state to the lease container, and it knows it has picked them up, and you will see that it will, the application has started, but it's just going to sit here now and wait for the next change. But if I go back now to our notebook, and there are the 2 items in the cart container that we wrote to initially. And here are the same 2 documents in the replica container, in the cart item container that were written by our microservice. So let's try an insert now. Let's say I now insert, I need 3 Surface Pros. And this is simply doing a create item with that document body, right? So I'm going to add that as a 3rd document. And you can see the microservice, wake up, and there's the upsert. And now if I query both containers, I'll see the same data in both. Now, it is the same data in both, but we understand, and the whole point of this is that in the first container, these 2 documents, documents number 1 and 3 here, or 0 and 2, if you will, they live in the same, oh, I beg your pardon. These first 2 documents live in the same logical partition because the cart ID is the same. And this 3rd document is in a separate logical partition in cart DEF. But these 3 same documents in this other container have these 2 Surface Pro documents live in the same logical partition for the purposes of querying by item instead of cart ID. If the quantity changes from 3 to 4, let's do a replace item, change the quantity from 3 to 4. There's another upsert. It happened very quickly. Under the covers is a feed poll delay that you can set. So when there are no changes, there's this poll delay because it polls. But once there are changes, it will drain those changes. So after it processes them, there's not going to be another poll delay. And there you can see, what was the last thing? I changed the quantity to 4, and you see it got changed in the last document in the 2nd container. And now the last thing to do is the delete by setting TTL to 10 seconds. So when I switch over, it just did a sort here. It picked up that app as a delete. It's not 10 seconds yet, or it will be if this doesn't respond. Ruin my demo. Come on. Hopefully it's not 10 seconds yet. It won't matter. If it is, it'll be gone. Yeah, it was 10 seconds because it was just sluggish to respond. I would have increased that to 15 seconds. So that got removed by TTL, and this got removed by our microservice. And that's replication. And yeah, I'm just going to plow ahead to our next microservice, which, if you attended my session in June, will seem very familiar to you. This is when you're dealing with relational workloads and coping with the fact that there are no joins and there are no relational constraints, and that you have to think about things differently in order to materialize relationships. And this was the topic of my June session. Very often the answer to do that is denormalization. And even if you're not in my previous session, this will all make sense to you. You'll see that what we're trying to do is basically cut down on the number of multiple requests that might be needed for our most common queries, without over-engineering things, making sure that our most common queries are satisfied by a single request. So a typical situation is if you would have product documents which has a number of IDs, as you can see here, including a category ID and an array of tag IDs, but you are missing the name of the category and the names of the tags. All you have are these IDs. The actual names themselves are stored in a separate container the meta container as category and tag documents, respectively. And in the relational world, we wouldn't think twice about this. We would just think of these IDs as foreign keys, and we just do a join, and we get, the information that we need all together. But we're not in that world. We're in a completely different world. So yeah, we can get all the products in a given category with this one query quite efficiently if we partition on the category ID, right? We'll get them all the products in that category, but they'll be missing the category names and the tag names. So we'll at least need this one additional query just to get the name of the category, which will be the same for all the products, of course. But then for each document returned by the first query, we will need to run this third query to get the tag names from that array of tag IDs. If this sounds painful, well, of course it is, and undesirable is an understatement. You just, we denormalize to handle situations like this. Again, if this was once in a while, if this occurred as a blip here or a blip there, as a part of some, back office operation, somebody's running some analytics, which by the way, there are many other better ways these days. There's a new Synapse link that's very exciting that we'll hopefully talk about in a future session. But if you're hitting hard with these queries, like your customers will be doing on your e-commerce website, then this is just not a good design. It's actually prohibitive. And instead you denormalize, which is just a fancy way of saying, in this case, duplicate data. Duplicate that master data. So the category names and the tag names that live in the meta container will be duplicated in every product. And we're not concerned about the storage concerns for that, like we would be in the relational world. And we're not concerned with the fact that we are denormalized like we would be in the relational world. But we have to still solve the same problem, like what if one of those tag names or category names change? So if I've got a product container with all of these product documents in it, and I've got a meta container with all of these categories in it and all of these tags in it, basically we want to listen to that meta container, because you can see on the right-hand side, I've got category name of shorts duplicated. And it can be duplicated many times for many other products in that category in the product container on the right. The same is true. Actually, I can do this. Yeah, right. So this name here is duplicated in many places, as are all of these names are duplicated from the master version on the left. So anytime there's a change, we need to pick it up with the change feed. And so, for example, if we change the name shorts to fun shorts, or we change the name tag, the tag name outdoor to outdoors, plural, we need to cascade that. Similar to replication, but it's one to many, because we have to update many documents that have the same ID with the changed name. And in the case of tags, it's a little delicate because we have to, update just a single item inside an array without, disturbing the rest of the array and stuff like that. But we can see how that works in a demo now. So you're going to see a similar pattern, and before long, this is going to be, seem very familiar, and hopefully also conveys how really easy this is to do. Here's my denormalized product function. Same pattern. Just decorate your public method with a function name attribute to make it an Azure function, and then use a Cosmos DB trigger to consume the change feed. And we're going to watch that product meta container for category and tag name changes using the same connection string. Now here I'm using the same release container. Now I told you we would dig into the release container in a bit, and we will. So let's stay focused here. The release collection container prefix here is again named after the product, and we'll see the significance of that when we look at the release container. But it's the same signature, the same documents come in. But it's very important to do exception handling. I'll pause for a moment and call out the importance of the exception handling. So whether you're using Azure Functions or the CFP library, it's going to be very important to have a pattern like this where you try catch each individual change. Because in the case of the CFP library, if there is an exception, it will retry indefinitely, which is fine for transient problems. But if there's something wrong with the data, as is often the case, then that same exception will get thrown forever. And if it's an Azure function, it will simply swallow the exception to keep that Azure function running. Neither of these is good, right? So you got to catch these things. And all I'm doing is logging output here. But in reality, the best thing to do instead of retrying, unless you really suspect a transient situation, would be to just, stash that ID away, stash a reference to that document away, or the document itself, to blob storage or a queue or a table, just somewhere to deal with later, another container, whatever, and just allow your microservice to keep pace with the events that are presumably flooding or potentially flooding your container. So inside process change, or I need to determine whether, here's another nice thing, right? Using dynamic, because some of these documents are going to be category documents and some are going to be tag documents, and they have different schemas and whatnot. So, but I know they always have a type property, right? So let's look at that meta container. Come on. I only have 2 categories, but I have 2 categories that's in one logical partition because we're partitioning on type, and like 5 tags, it looks like, okay? All right, and we are partitioned on the type property. All right. So basically, I have to cascade these changes. If it's a tag or if it's a category, if in the case of a category, I am going to query for all of the products in that category. This is a single partition query since the category ID is known. So in my options, I say I know what the partition key is, and therefore that makes this a very efficient query for all of the products in the product container that are in that category. And the pattern is always that you get an iterator, that you iterate as long as there are more results, and each iteration of the iterator gives you a page of results that you get with read next. And then each page in turn has documents. And then each document that is resulting from the query is going to get updated by modifying the category name in memory and replacing the document in place. In the case of a tag name, it'll be similar, a little subtly different in the sense that in our options this time we don't have a partition key because we are finding all of the documents that have inside the tags array containing an object with an ID matching the ID of the tag that was changed. And that obviously is going to span logical partitions. It's a cross-partition query. How often do tag names change? Presumably not so terribly often. So that makes this perfectly fine. Again, warning you against over-engineering it to completely eliminate cross-partition queries because you'll never be able to completely eliminate them, and that's fine. This instead says, tells the SDK to parallelize as best as possible the cross-partition query to help speed it up. But otherwise, it's the same iterator and page looping pattern like we saw. But for each document that we want to change, we want to find the one item in that tags array matching an ID, then update just that one item in the array by changing its name and then calling replace as well. See it work. Let me do a quick time check. Yes, I'm doing it on time. All right, so let's go ahead and see how this works. I'm going to have a look at my product container here. It's going to be the same example we saw on the slide. So I've got several documents that are in the shorts category where I've duplicated the name. I've also got in the tags array outdoor repeated for TOD, that sort of thing. This is the master data in the product meta container, right? So anything that changes here, let's start our denormalization service. Now, actually, our denormalization service is actually still running. Why? Because I've got both Azure Functions in the same project, which is actually not a good thing. Okay, I'm just doing it because I can, and we'll talk about why it's not a great thing. It's not terrible. They're still independent, but think about it. They both live in the same project. So if one fails to compile, the other fails to compile. And if you deploy one, you're deploying the other. You can't deploy them separately. So that, for those reasons, it's not the best practice. But I've done that here. You can see it picked up 2 functions, all right? And hopefully this is going to work without me having to restart it. I'm going to rename the category shorts to fun shorts. So I know the ID of shorts. That's the ID of shorts. I'm going to change the name to fun shorts. That's the idea of outdoor. I'm going to change it to outdoors, plural. Okay, so let's give that a run. Let's see if our microservice wakes up. Yep, it's waking up, executing denormalized product. Yeah, and it cascaded several documents. 3 documents, actually 3 different documents in each case, where the tag name was present or that category name was present. And now if we look at our metadata container, there's our change that we made into the master data, fun shorts, and now outdoors plural. And now if we look at our products, you can see the change has been cascaded fun shorts in 3 places. And outdoor is now outdoors, and there's one more, we just can't see it. You see, I told you, it's being displayed tabular only because we're inside of a notebook. A regular, these are really JSON documents, and you're getting to see only the top level scalar properties as columns, and anything that's complex or nested, like an array or JSON, you just can see the raw JSON, okay? All right, so you saw that work. Hopefully you're seeing how powerful and easy this is. I'm going to close down this microservice, and now we're going to take a peek inside that lease container. We have 2 independent microservices, and they could be consuming the change feed at different paces, but they're sharing the same lease container. What is inside this lease container? This lease container is holding bookmarks. You can see I've got 4 documents in there, 2 for each microservice. So the way this works is for every microservice is going to be like just a metadata document, and then you're going to have 1 document for every physical partition. This is a tiny container, so there's only 1 physical partition. So if I look at the denormalized product, if I look at this one here, let me look at this one first. This is the metadata one. So this, you're always going to have 1 of these, and then you're going to have 1 of these for every physical partition. And this is a tiny container. There's only 1 physical partition ID, and a timestamp. And you do not need to understand this content in here. It's managed for you automatically by the CFP library. But what you can see is that by using that I'm tying it back around to that lease collection prefix or that lease container prefix. The ID of all of these documents is prefixed by that prefix, allowing me to get that isolation that I need to share the same lease container, not require 1 lease container for every microservice. That would be very undesirable, right? So we can and this lease container, even in heavy production environments, is often adequate at the smallest manual and the smallest provision throughput of 400 RUs. Okay, and you typically partition on the ID. It's a tiny little container. Okay, so now we're gonna ratchet this up. Okay, we're gonna take this to the next level. We're gonna go into some bulk with a much larger data scenario. Contoso Airlines. We're a small airline. We have 12 flights. We service out of 6 airports across the continental US. We hope to expand, but even at just 12 flights, that's a lot of telemetry. And we are going to use Cosmos DB to store all of our telemetry and hopefully accommodate much more growth in the future. And we have a number of requirements. Some of them are obvious. We'll need real-time flight info. We're going to want that. Every plane is broadcasting its telemetry. We need to see where each plane is in real time. We'll have certain no-fly zones that will need to be alerted to if a plane enters. We'll need arrival boards to show at airports and other clients, for arrival information, grouped by destination airport or by arrival airport, I should say. And we can never throw this data away completely, forever. Let's say that's a compulsory, it's a government regulation. So our solution is, well, I'm going to show you how we first of all ingest that flight telemetry, and then we're going to implement microservices, as you might have guessed, to give us those email alerts when a plane enters in a fly zone, to give us materialized views that make it efficient and cheap to query against what really is a huge volume of data, especially when those queries are fast and furious and frequently invoked by a large number of clients. And we're going to solve our permanent archival requirement by offloading data to blob storage, cold storage. So this is really much more about responding to the events as we ingest and not how we are ingesting. So I'm not going to spend a lot of time on this, but we're going to have a container called the location container. And I have a simulator, because I will confess I don't have my own flight of airplanes, but I have created kind of a very cool little simulator that kind of simulates the real world for our 12 flights. And it's going to generate all the telemetry that's going to get ingested into the location container, and that information is going to include the obvious things: how fast the plane is going, the altitude, speed, altitude, duration, and of course latitude and longitude for the location, the current location. And this is fast and furious. We're broadcasting this. Every plane is broadcasting this every 10 milliseconds. So it's a lot of data that we want to ingest. And if you recall, we had common partitioning patterns. This isn't the only way to do this, but we're going to go on that ID property, which is going to be a GUID. And that is going to allow us to scale elastically and keep pace with this velocity and volume of data. But that does mean we're going to have exactly one document per logical partition. And since the ID is a GUID, we'll never be able to do a point read on it. So, but we're not worried about that. We're worried about writing. We want to optimize for bulk loading of this telemetry in real time. So let's see our flight telemetry generator in action. Contoso Airlines has this flight telemetry generator. I'm going to run it. I am going to show you that I've got, come on, don't fail me now. Thank you. 6 flights. These are 6 flight documents in one of my metadata in my meta container, and I'm sorry, 6 airports rather, 6 airports and 12 flights. Okay. If you look at the destination side, we actually only are arriving at 4 distinct airports. All right. Now I'm going to generate some metadata. I'm going to say G and then -C for continuous. With continuous means that as soon as a plane lands, it takes off right again. So this, I can run this for days and hours. And one thing that you can see, one advantage that Contoso Airlines has, we fly faster than everybody else. If you look at the remaining duration on these, we're really actually going to be coming in pretty quick. Actually, oh no, I'm sorry, I meant remaining. If you look at the remaining going down, right? So we're going to arrive, but then we're just going to take off again. So how are we doing this? Now, I'm not going to get into all the code for this generator. Like I said, I put a lot of nice things in there to make it simulate the real world. But it looks like my arrives column, I broke something there. But what you can see is that I'm loading data. I'm not quite 10 milliseconds. Not quite every 10 milliseconds per flight, but I'm still doing pretty good at 100 per second. Actually, it goes faster when I'm not presenting. Well, I'm going to show you just only 2 parts of this generator while we well, let's just actually pause it or stop it. Inside the generator, at the bottom of this region, this is the bulk insert method. So what I'm doing is I am calling this method once every 10 milliseconds, and each time I'm loading that up with 12 documents. So every 10 milliseconds, I'm writing 12 documents. And the way that I'm able to saturate the throughput, I provision 10,000 request units on this container. And the way that I'm able to saturate that throughput on a single machine is by using an array of tasks. So this is a kind of a bulk loading pattern that you can use, where you, instead of calling await create item async to insert one item at a time, you just call create item async without the await, and that just gives you a task. and you load all those tasks up into an array, and then you just await all of the tasks in that array, and that's how you kind of can saturate the throughput on your container and do kind of bulk loading of data. All right, so if we flip on over to that location container and have a look at the kind of telemetry that's been coming in. Gonna close these guys down, we don't need these anymore. And I look in the location container. Actually, come on. I wanted to show you how many documents I have in there. I've been running this for several days. $29 million documents. Okay, that's respectable. It's still only giving me 2 physical partitions, but you know, there's really lots of room to grow. And if we look at the items, we can see what each of these telemetry documents look like. Remember, we're partitioned on the ID property, and the ID is a GUID. I'm set the type to location in every document just to identify this as a location type. But that's the flight number, that's the tail number, which is like the specific aircraft departure and arrival. This is the general information about the flight that doesn't change. And then here you start the telemetry, the current latitude, longitude, altitude, speed, remaining minutes, remaining miles, and so on. There's a time to live on there, which is going to tie into our last microservice. So we'll keep this around. That amounts to 30 days. In seconds, that amounts to 30 days, after which this document will be deleted. But we're going to have an archival microservice to archive this off to cold storage, which we'll look at later. So that's my generator. And now let's get to our first requirement, those no-fly zone alerts. This is going to be very easy. We'll have a microservice that watches each event, that watches each of these documents that we just saw, and it's going to do a spatial query. It's going to examine each one and run a spatial query and issue those alerts when a flight enters a no-fly zone. Let's see that. Let's see the microservice for that. Now this should start looking very familiar, but you look in this case here, I've got one project per microservice, which is a much better practice. So they will all compile independently, they will all deploy separately, giving them that independence. And we're looking now at the email alert microservice, which has just that one function in it. Before we look at the statics up top, look at the familiar pattern from before. A function name attribute that makes this an Azure function, a Cosmos DB trigger attribute. This time I'm using a constant, but you see this is the location container. That's the same container that we're flooding with telemetry data. We have our own lease container, and then that important lease collection prefix to isolate this microservice from other microservices sharing the same lease container. The same set of documents and a logger to write output. We're going to check each flight location. So we're just watching here. We're not storing any data. We're just watching. And so now look at these statics that I have up top. I've got a spatial object. It's my business logic that lets me do intersections and distance queries and that sort of thing. I've got a SendGrid client, and if you're not familiar with SendGrid, that is a super easy way to send emails on Azure. It's a super easy to use service for that. Now we can pause and ask the question, should my microservice be burdened with the actual sending of an email? And the answer is really no. This is a demo, and so I'm sending the email from my microservice, but really the primary concern of the microservice is just to detect if you're in a no-fly zone, and if you are, to trigger a notification, whether it's email or SMS. I mean, it could be, or both, that should be irrelevant, and handling failed deliveries is not a burden that should fall on the microservice. It's minimizing the possibility for exceptions to occur. But having said that, I am sending the email, so I'm going to have a from email address, and a from name, and who I'm sending the email to. And all of that is with environment get environment variable pulling from local settings JSON. So in addition to the connection string that we saw before, please don't memorize this, so I'll just have to change it. But that's my SendGrid client for sending emails. The emails will come from Contoso Airlines alerts sent to my Hotmail account. All right. Now also notice I've got local ports set here because what you'll see is that in the other three microservices are going to use ports 70, 72, 73, and 74 respectively, allowing me to locally, like run the full orchestration of all my microservices simultaneously as I ingest telemetry, which is a very nice experience. And debug and test and troubleshoot all your microservices concurrently by running them each on unique ports. So for every document that comes in, we just want to check that flight location. Well, this time I know the schema of every document. I know the type. I don't want to work with a dynamic. I've actually got a location event class with camel case JSON properties mapped to the JSON document in Cosmos DB. So I have strong typing now, which is much nicer, right? When you know the type. And I'm calling spatial. Now, actually, let's talk about these constants, these statics just a little bit more. We are relying on state. We are relying on state in the sense that the first time our Azure function spins up, the constructor fires this all the newing up here occurs during that construction, and then during multiple invocations, it doesn't get newed up again. It's reusing the same state. So here's a dictionary which I failed to explain. Once a plane enters a no-fly zone, we need to trigger the alert right away, but we do not want to then trigger the alert once every 10 milliseconds, as long as that flight remains in the no-fly zone. Do you think you want to flood someone's inbox like that? Certainly not. This is a throttling. There's many ways to do this. I'm just using a dictionary to throttle. So once you are in a no-fly zone, you will. Our microservice is not going to send another email for that flight unless it's still in the no-fly zone a minute later by having this dictionary keyed by the flight ID and the last time an email notification was sent for that flight. So I'm relying on that state being there. Now, if the Azure function goes down because my planes aren't flying, which is unusual, my planes are usually flying, still the Azure function can go cold, all these statics will get lost. Well, the next time it fires up, they'll just new up again, and that'll be fine. So we check the flight location. Is it in a no-fly zone, passing in the latitude and the longitude? And for the very simple purposes of this demo, a no-fly zone means that you are within a 150-mile radius of Washington, D.C. In the real world, you would have no-fly zones in the database, and you would be doing intersection queries. We're just doing a simple distance query and returning true or false if you're within that 150-mile radius. So that's our no-fly zone. So if you're not in the no-fly zone, then we return out. We just don't do anything. We like essentially swallow the event. It's like we don't care about it. Otherwise, and we need thread safety. So if you've ever done multi-threading, you understand that in between the time that you check the dictionary for the presence of a key and the time that you add an item based on the fact that it's not there, that needs to be in some sort of semaphore or some sort of synchronized locking mechanism. And here I'm just using a simple thread locking object to achieve that. And you just need to be keenly aware that all of your microservice code is multi-threaded because you're getting the benefits of the parallelism behind the scenes. So as the events are flooding the change feed, you're getting scale out, right? So if you look at the main method here, this could be just one document in it if there's a sporadic change, or it could be just a small portion of a much larger set if there are tons of changes coming in and things are being split out across multiple instances of this function. All of this is doing is basically saying if it's less than a minute, you're in the no-fly zone, but it's less than a minute since I sent an email, then I still want to return. Otherwise, I want to send the email. And again here, I mean, there's logic in here that I'm not going to get into, but you see there's HTML, and there's some like extra code down here to make the email look pretty with some HTML. Now, it's just more potential for exceptions. Again, the burden of doing this should arguably fall on some external logic app, where we should really just be queuing to that logic app or to some other, service that's going to handle the notification. But, this is just a demo, so we're doing it all here. All right, let's see it work. So that means multiple startup projects, right? And that's going to be the generator, as well as the email alert microservice, which I'll start. Yeah. And it's not going to take long for us to get an alert because, as it turns out, our planes routinely fly over the no-fly zone. Here's the Azure function. And it is listening on port 7071. Let's get our planes in the air. Oh, you see the yellow? Let me pause it. Hopefully I can catch that. Oh, there we go. There we go. Flight. Oh, and I just got an alert. I'm opening it up right now. In Outlook, here it is. There we go. You see it working. And the flight, if it's still in the fly zone in a minute, then I will get another email alert. Close that. Close that. Our next requirement, querying real-time flight data. That should be easy, right? It's all inside that location container. We can do a top one query like this for any flight. Ordered by that timestamp descending, top one should give me the latest document per flight, and that should be able to do a map like this, right? Okay, so I'm going to show you some eye candy that I've built for you, and laugh at me if you must, but this is actually Windows Forms, okay? All right, let's shut this guy down, shut this guy down. And let me just add another project to our starter projects. And include the desktop, which it's a WinForms app, but it uses the WPF control for Bing Maps because there is WPF interoperability in WinForms. And I just can't let go of WinForms. So I'm definitely not going to dive into the code for the desktop app, except for the parts that are actually running the queries. Okay. Oh, actually, I'm sorry. Yeah, we don't need the email alert service right now. All right. So here's my Bing map. I've pulled in all the flights listed on the left. I have pins for all the airports shown on the map. I've done that by, like I said, I'll just show you the data access code, which is in my repository down here. Those are small lookup lists where we're partitioned on the type property, and the type is either airport or flight. So I just call this generic get list, getting all the documents for that type, and we know what the partition key is, and that's how I got, my list of airports and flights. Now, I'm going to get my planes into the air, run continuous, and let me watch my flights now. Let's start with one flight. Oh, that's pretty cool. And there it is going in real time. We see it. Oh, actually, that was left over from before. Okay, so the telemetry, the flight has just taken off, and it's moving along nicely, but I'm running these queries every 3 seconds on the client side, and what's it costing me? 66 RUs every 3 seconds. If you're not already familiar with Cosmos DB, and you don't know if that's a lot or not, let me tell you, that's a lot. And you can see it racking up very quickly. And I'm just one user, okay? But because I'm running that top one query. And it just gets worse when I add a second or a third. But it's pretty cool. If I hover over each plane, I get real-time info in the tooltip, right? These queries are very expensive. And that's because these are all cross-partition queries, right? We're querying a mountain of data for we at most ever need 12 documents. And that's where materialized views come in. So we see how expensive it is to query over that mountain of data. Instead, we'll build a materialized view and do it much cheaper. We'll create a tiny container with just the 12 documents in it. That's the simplest kind of materialized view. We're not doing any transformations. We're just preserving the current one that we care about and leaving all the other ones out. And it's going to be a small number. So we can partition on the type property, which is set to location, and all the current flight information for all the planes can be in one logical partition. And that ID that's a GUID, well, we'll just set it to the flight number. So we'll know the flight number, we'll be able to do point reads, and the result is going to be extremely cheap. Here's the microservice. The current location microservice. Look at local settings JSON. It's on a unique port, right? So it can run independently. And the function itself should look very familiar to you by now, with the familiar function name attribute and the Cosmos DB trigger attribute, watching the same location container, using the same lease container with a unique prefix, getting the documents that changed, getting a reference to my target container, which is the current location container, which is the materialized view container, and just calling update current location. Now, I don't need to keep this up to date every 10 milliseconds per flight. I'll have a similar throttling logic using a dictionary, right? So inside of my should skip event, if it's been less than 3 seconds, I'm only gonna update the materialized view once every 3 seconds, not once every 10 milliseconds per flight. It'll be once every 3 seconds per flight, which will be more than adequate. Otherwise, it's just needless to spend that extra, all those rights. But look, there's one event that I'll never want to miss, even if it's less than 3 seconds. When the plane lands, you're going to get this document once, and you are guaranteed never to miss an event out of the change feed. So in order to make sure that you don't miss it by your throttling logic, I'm just returning false here. So we'll never miss is complete. And now we'll just include that to start up as an additional microservice alongside the email alert microservice, because of course, current location. They're on distinct ports, and they're each watching the same change feed on the same container, using the same lease container for state. And now I'm going to hit Control F5, spin them all up. There's the generator in the upper left. Here are 2 microservices starting. Here's my flight map. I can check Washington, D.C. to put a circle around the no-fly zone so I can know when to expect those emails to come in. And you can see they're running on separate ports. This is port 7072 for our current location microservice that we're looking at now. Okay, this is picking up changes since the is actually correct. It'll eventually stop when it catches up, because I stopped the microservice, but still generated more telemetry. There we go, it caught up. Okay, we'll minimize that, but you see they're both running concurrently. And let's start off again. Let's start off with one flight. Get our planes in the air. And let's look at one flight. And it's, like I said, like we saw before, 66 RUs. But if I say use the materialized view, you can see the plane flying. Uh-oh. Dum. Looks like this microservice is not working. I think I actually Oh, yeah, there we go. Sorry, my bad. Come on. There we go. I was holding up the console window. You see it's upserting. You see the yellow going by, but only once every 3 seconds per flight. And there you can see, I'm getting the same behavior. But what's the cost? Let's see, for one flight, what's the cost? 1 RU. Nah, that's dirt cheap. That's what you call dirt cheap, right? Because it's a point read. I'm not doing that select top one query. I know the ID, which is the flight number, and the partition key, which is always location. So I'm just doing a point read. Here's the code for that. The UI, when I check that checkbox, I'm getting no fly zone alerts as we speak. Instead of running that expensive top one query, it's just doing the point read, given the flight number and the partition key. And as long as you're under 1K, the cost will be 1 RU. So check it out. It's very cheap. It's only 14 RUs. 2 flights, well, that's 1 RU. It's now 2 RUs every 3 seconds. Makes sense. Still pretty cheap. 3 flights, that's 3 RUs every 3 seconds. And that also makes sense. And I'm sure you can figure out that if I do a 4th point read, that'll be 4 RUs every 3 seconds. But watch what happens when I do that 4th flight. Now I'm doing a query that costs under 4 RUs. There's a point of diminishing returns where they all live in the same logical partition. So querying for multiple flights within that logical partition, the ones I checked off, costs only 3.35 RUs. And the cost goes, which is less than 4, which, shaving off those RUs, which we're always trying to do. But the savings become even greater now when I go to 5 flights. Now it only went up to 3.48. Let's go to all 12 flights. Only 4.45 RUs instead of what would be, let's say, 12 RUs if we did 12 point reads. So dirt cheap. And just to shock you into the reality of this, again, I'll uncheck use materialized views with all 12 flights. And I'm just one user. And look at them rack up. They're in the thousands already. As I'm barely speaking, and they're in the thousands. And before long, I mean, this is prohibitively expensive. If this doesn't sell you on the value of materialized views, then I don't know what does. Now, in the interest of time, I'm not going to dig into the code for the next microservice. I'm just going to explain it because it's conceptually similar. We want an arrivals board. Let me stop these down. And also, in the interest of time, I'm not going to, seems to start out much slower when I start all the microservices up concurrently. I've kind of proven to you that I can do it. So we're just going to run one microservice at a time for the last 2. For arrival data, it's going to be the same concept. We need grouping logic to get all of the flights that are landing in a particular airport. And it's expensive to do that every time we're querying for real-time arrival information. Instead, we'll have a materialized view. And again, another tiny container with documents that look like this. This is the LAX document showing the flights arriving at LAX. It's there ready to be served, being materialized in real time by our materialized view being generated by our microservice. So I'm not going to go through the code that shows the grouping logic, but it maintains this materialized view in memory in real time. And it persists it like once every 5 seconds, but it maintains it in memory. Right? And there's a similar logic as you've seen before. So here's the microservice. Arrivals board. Running on port 7073, where all it's doing, and again, I'm not digging into the code. Update board here. This is what's doing the grouping in memory. And then once every 5 seconds, using that thread lock, we are, we're upserting that item to the arrivals board container. And so now I'm going to set that to start up as well. And I'm going to turn off the other ones to make it a little faster. So we don't need to see we want to see the arrivals board now. We don't need to see current location anymore. We don't need to see the email alerts anymore. Let's run. While that's coming up, if you go back to the portal and you look at the current location container, the one that doesn't have 30 million documents in it, but rather just 12. Here they are, as they were last written by our microservice. Here are the 12 documents that make up that materialized view. Come on. There they are. Uh-oh, what did I do? I don't think I didn't close down something from before. Try that again. Get our planes in the air. Our Azure function starts up. We'll go to the arrivals board. Let's look at the flights coming to JFK. Well, it looks like the microservice is still starting up in the background, so just give it a moment for the UI to pick up the data. You start seeing yellow go by. There we go. It's usually not this sluggish, just again because I'm presenting, but there we go. Now that's a single point read, just costing 1 RU, even though it's for 2 flights, because it's an array of flights. Like LAX has 4 flights coming in. It's 1 RU, because there's an array of flights and they're generated by our microservice. All 4 airports that we have flights coming in, it's 4 RUs every 3 seconds, because we have that cheap materialized view to query from using point reads. And if you look inside the container, oh, this one here, the arrivals board, here is that materialized view, those items, which will come up in just a moment. I'm going to wrap up now with our last microservice for our last requirement. Very simple, very straightforward. Archiving to cold storage. See, here's that materialized view. The flights coming into LAX, all being kind of generated by in real time by our microservice. And our last requirement is to offload to cold storage. Let's look at that data archival microservice that is running, on port 7074. And in addition to my Cosmos connection string, I have my storage account information. So this account already exists, but this blob container does not. It doesn't exist yet. Flight history, let's create that. Now remember, there's a TTL property on these documents that's making them expire in 30 days. So in 30 days, they're going to expire, but we need to have a permanent archive. So let's go to my blob containers and create a new container. That's the name. And if you look at the microservice itself, again, timestamps, because we don't need to archive every telemetry document that we're getting every 10 milliseconds. It's adequate for us to just every 15 seconds for permanent archival purposes. So we're not going to really, flood our blob container the way our IoT telemetry container is getting flooded. We're just getting a reference to our storage account, and right inside here, we're just calling archive flight location. You can see what it's doing. It's just deserializing. It's checking if it should skip, using the same logic to throttle every 15 seconds, but never miss the is complete event, even if it's less than 15 seconds, and writing to the blob container. Here I'm constructing the name of the blob, and again, it's every 15 seconds. So let's run this. Oh, there we go. And that would be the data archival microservice. I'm going to turn off the arrivals board. I'm also going to turn off the desktop. We just need the generator and the data archival microservice. I fast-tracked the slides to end on time. I knew it was going to be about 90 minutes, and it looks like I'm spot on. So just going to run this demo and wrap up the deck and let you guys go. Or actually, let you go at me with questions, I should say. Data archival microservice running on port 7074. Get our flights in the air. There, you can see archiving to blob storage, and that'll go by every 15 seconds. You'll see more. Let's go into the container. Yeah, just slowing down on me because it knows we're wrapping up. But here you can see the first 12 documents rather. If I think that now that it's been more than 15 seconds, if I refresh, yeah, you can see a 15-second gap in between each one. And these are blob storage documents. I open up any one of them, it is showing the telemetry data that we permanently archive. Always go back and know where our flight was at any given time within 15 seconds. So with that, that is a wrap. That covers all of our microservices. Let's just see if I have anything else I wanted to leave you with. There's the blob document. Shut this guy down. And so with that, I want to thank you, and I want to thank Mark. I know it was a bit longer than we usually run, but I hope you found it useful and comprehensive, which was my intent, but still approachable and digestible. With that, I'm going to open the floor. I'm here as long as you need me to be with questions.
Excellent. Thank you very much, Lenny. My mind is officially frazzled now after that much, which is a good thing. It's frazzled in a good way. I'd often say this. I'm looking forward to watching this session again, and I definitely am in this case. I think it will be really useful to go over.
Well, I'll tell you, it's a much slower on the Pluralsight course.
Yeah, well, I was just going to say it's probably a good segue just to say that if anyone enjoyed that, and I'm sure everyone did, it's worth checking out your courses on Pluralsight. You've got your 2 new ones published there, and as you say, you go in a bit more depth as well into all of this, and there's a bit more time to rewind and whatever, so definitely worth checking those out. So I've got a few questions. You focused a little bit on the RU and the cost of the queries, and I guess as a developer you've got to constantly think about, well, confirm that whether you agree with this. You've got to constantly focus on what your intention is and what the RU count is. Is that kind of what you'd expect a developer to be doing?
I would expect the developer to be aware of the queries that they're writing, and they would kind of have to be, because you're writing a cross-partition query when you don't supply the partition key in the options. And when you're doing that, the developer should be aware of the frequency of that query, how often, what is the usage pattern? It all comes down to understanding the usage patterns and making sure that your most common queries are A, scope to a single logical partition. It's okay if the edge cases aren't. And B, in most cases, you get everything in one document by denormalizing. You don't have to query multiple documents. And those are the things the developer should be thinking about. All of those things will bring the RU charge down. You run cross-partition queries on very large containers very frequently, then the cost will rack up very quickly, like I demonstrated with the materialized view.
Excellent. Just slightly leading on from that, is there any kind of automated analysis tool that you can run against what's going on to tell you that you've got your partition key wrong based upon your query patterns?
Oh, okay. There's the metrics tab that will show, it has a heat map to help you identify a hot partition. I've not actually seen it. Maybe I've just not been able to simulate it. Like I said, for my container, I've only got 2 physical partitions. And because of the way I'm doing everything right, I'm not going to see any heat map. Let's go switch to our Contoso Airlines location container. That's the big one. And look at storage first. So here are my 2 partitions, my 2 physical partitions. Maybe it's under throughput. There's a heat map here somewhere. Or maybe I just haven't had enough activity.
Yeah, maybe it requires a certain duration.
Yeah, and it says select a part. There it is. There it is.
Cool.
I told you it was there somewhere. Yeah, but reading that is another story. So, in terms of picking the wrong partition key, it could be the wrong partition key from a storage perspective or from a throughput perspective. Where it's even distribution from a storage perspective, but it's like if you pick the creation date, for example, then all your rights, that's a hot partition, and this should reveal that.
Yeah.
But you got to monitor your RU charge. You got to keep an eye on these metrics.
Excellent. So you're talking about logical partitions and physical partitions. Presumably the physical partitions point to multiple logical partitions?
Right. You've got multiple logical partitions in each physical partition. A physical partition can loosely be thought of like a computer, like a box with a disk and CPU. It's more than that because it's also a unit of replication for high availability, but it is fundamentally that. And Cosmos DB shuffles them behind the scenes, shuffles the logical partitions around behind the scenes as it splits each partition the way I showed.
Okay.
Logical partitions are always self-contained will never span physical partitions.
Okay, fantastic. So you're talking about the change feed. Is there a change feed per container or is it per database?
Container.
Okay. In the case of a globally scaled Cosmos DB, presumably the change feed is also distributed?
Correct.
Okay, fantastic. What languages can you use to develop against a change feed library?
Others, I'm almost certain Java and Python. In the earlier days, today the CFP library is baked into the .NET SDK, so which is the most full-featured SDK and the only one that I really use and I'm very familiar with. I know that there are SDKs for all the other languages too, but they have varying levels of support for things. So how much or how little change feed processor library support there is in the other SDKs, I can't vouch for it. Today it's baked in. You install the .NET SDK and you get the change feed processor library. I'm almost certain you can do it in Java and Python. Almost certain, and other languages.
Yeah.
And by the way, it's not for the other APIs, right? It's also available for the Gremlin API and for the MongoDB API. That's actually more significant than the SDKs, right? Because not everything is always available on every API.
Yeah. Excellent. So when you picked up changes from the lease container, you said that the state is written back so they aren't picked up again. I think you demonstrated that. But what if your client crashes when it's handling those changes? Can we implement some kind of checkpoint to say that things have been handled?
Well, you would manage that checkpoint yourself. I didn't actually show you the lease container in the end in the Contoso Airlines database, but if you look inside the lease container here, because I have 2 physical partitions, there are 3 documents per microservice, each isolated by their own prefix, and one of them is that meta document. And yeah, this is not, so this is the timestamp. So this is when internally the change feed processor library last checked for changes. It has served you the changes. Now, if you swallowed them, so to speak, like you didn't handle the exception properly, or you crashed, you saw how I did start from beginning. You can start from any arbitrary point in time. This is actually a very compelling aspect to using the change feed. It goes back to the beginning of time. Jet.com, that was bought out by Walmart recently. You can see there's a case study where they're doing exactly this, and they recover from more than one disaster by just rewinding the change feed and letting the events play over because the microservices were all messed up the first time these events were processed. And even though in the time that elapsed since the event originally occurred, there's been partition splits and logical partitions have been shuffled around, the order of the events per logical partition is still going to be guaranteed. It's a lot of nice aspects to that.
So from what you say, does that mean that, let's say, for instance, you got a small Cosmos container, it's not got much data in, but there's been lots of change over a very long piece of time. Does that mean that essentially the storage that the container or changed data takes up in the change feed is just constantly getting bigger and bigger? I mean, wouldn't there be a cost impact?
That's a great question, one that I think about. I would like to talk to the folks on the team a little bit more about. I mentioned that interim updates are currently not preserved. So if you think about it, it could very well be, I don't really know the internal implementation, but the way it is today, since deletes are not preserved, meaning when you delete a document, it's just gone with no record of it. And interim updates are not preserved, so when you replace a document, the previous versions are lost. It could be entirely true that the change feed itself is nothing more than pointers to the actual documents and not a duplicate copy, but just in the correct order. And once you start preserving interim updates as well as deletes, well, now you need a storage mechanism to handle that bloat, as you say. And I guess, my guess is that when you enable deletes and interim updates, when they make that possible, that you will see that increase in storage requirement. But I think that today, I would guess that today they're being much smarter about it. There's only one instance of a document in the change feed per every document in the container. It's just that it's just the order that needs to be preserved, and so the data itself does not necessarily need to be duplicated in the change feed. But this is pure speculation on my part, just to be sure. But I'm going to find out more.
Okay, cool. If someone came to you for a requirement for a near-time data reporting solution, presumably Cosmos DB and change feed would always be your first port of call over other databases, for example, SQL Server using CDC.
Okay, that's a lot that you just said. But if you want to break it down in terms of what you would use for analytics, like you would jump to use the change feed to serve your analytic reporting needs on Cosmos DB. Actually, it's in preview now. There's a new Azure Synapse link expressly for this purpose. It's rather groundbreaking in the sense that it makes all of the transactional data in Cosmos DB. It makes a column store representation of that data available in near real time, meaning 5 minutes or less. And then there's a link from that to Synapse for you to run Spark or SQL queries. The thing is that new Synapse workspace where you can do that, that's also in preview. And to date, you can only do this with Spark, which is not really my thing. So I'm still waiting for GA, which could be a while. But the promise then is that you will be able to run your analytic queries using SQL in Synapse, like data warehousing SQL queries, against your transactional workload, with a zero impact on your transactional workload, because you're actually hitting the column store version of that workload that's kept in sync within 5 minutes. And that's a very compelling story for real-time analytics, where sometimes you have to wait hours or days to get real-time data out of our transactional workload. They say that it's zero ETL. This a marketing hype to some extent. There's always some ETL in some form, but this is really streamlining it. Using something like Synapse Link, because ultimately you're still running queries on your transactional workload, right?
Yeah.
So it's not a silver bullet. It's groundbreaking. Like a Lamborghini is just so much better than a Prius. Right, but neither of them are going to take you to Mars. right? They're both cars at the end of the day, right? I would say that there's time to tell for the analytics story with the new Synapse Link and Synapse Workspaces. But yes, today you can, and people do use the change feed for more than what I've shown tonight for doing real-time stream analytics, right? Stream processing over the data as the events are fired.
Perfect. Okay, then that concludes the questions. Lenny, thank you very much. The session was amazing, as I expected. Really appreciate you
love doing
speaking.
it, and I want to thank you guys for attending, and I want to thank you, Mark, for hooking it up.
Anytime. Right, thanks a lot, everyone, for attending, and hope to see you all soon.
Everybody stay safe and healthy. Bye now.